Can we do concurrency control without locks? What other techniques are there that we can use? How do we use timestamps to make sure that our schedules are serializable? And what are the pros and cons of any techniques that do not use locks? For these questions and more, let's dive in. Hello and welcome. My name is Elhelw. In the previous videos, I have been talking about concurrency control. Mainly, that's the way to make sure that transactions execute in a way that is serializable. And we've talked about what it means to be serializable before, so please watch the previous videos. I'll put the links in the description, so please refer to them before continuing with this one. The technique that we focused on the most to ensure serializability in the past was by using database locks. We talked about different kinds of locks, like shared locks, exclusive locks, and so on. We talked about a mechanism known as two-phase locking, which ensures a serializable schedule. We've also seen some pros and cons of this mechanism. We've seen some problems that may happen when you use two-phase locking, such as deadlocks. And we talked about how we can resolve these problems using techniques like deadlock prevention and deadlock detection and so on. One of the deadlock prevention techniques that we talked about in a previous video used timestamps along with other things to make sure that deadlocks do not occur. So today we are going to start talking about some other concurrency control techniques that do not use locks at all. They may use things like timestamps as well, or maybe some other information there, but they just do not use locks. So they do not wait for each other in the same way that the previous techniques were. So with that, let's start with the first technique for today, and that is known as timestamp ordering. Timestamp ordering, like I said, it's a concurrency control technique that does not rely on locking. It uses timestamps, obviously. It has to do some checks, some validations to make sure that transactions execute in a serializable manner. One note is that timestamp ordering, to the best of my knowledge, is not actually used in any of the major database systems. It's more of a theoretical technique, I guess, but it can also be seen as the foundation or the basis for some other techniques that are used in practice, which we will get to further on. So it is important to understand what timestamp ordering is and how it works. Timestamp ordering, like I said, it relies on timestamps. So each transaction is assigned a timestamp, and these timestamps have to be monotonically increasing. This is one of the conditions for this to work for the particular checks that we will get into in a bit. But basically the idea is, first transaction gets some timestamp, second transaction will get a higher timestamp, and so on. So if we have two transactions, Ti and Tj, and the timestamp of Ti is less than that of Tj, we want a schedule that is equivalent to a serial schedule where Ti runs before Tj. So timestamp ordering tries to enforce a schedule like that based on the timestamp. So like where the lower timestamp transactions should come first. And if at any point it finds that it cannot produce such a schedule, then some action has to be taken, like aborting a transaction and so on. So we will get into the details, but this is the high level idea. So one question to ask is, how are these timestamps assigned? One simple way of assigning timestamps, there are multiple ways, but one of the simple ways would be to use the system clock or the wall clock. So whenever the transaction starts, see what is the value of the system clock and let that be the timestamp for this transaction. These are monotonically increasing, of course. Also, it guarantees that no two transactions will get the same timestamp because usually these system clocks have granularity all the way down to the millisecond, or sometimes even more granular than that. The only way this would not work is when we start going to, let's say, distributed databases and so on. You may have multiple servers. Maybe their clocks aren't in sync, so there might be differences. You might end up with a timestamp that is not monotonically increasing, which is a problem. Another way of doing timestamp is by using a simple counter. So just every time the new transaction comes in, you increment the counter and you use that value as a timestamp. So the first transaction has timestamp value of 1, the second transaction has timestamp value of 2, and so on. And of course, this requires being able to read the counter and increment it atomically, which is usually something that most systems have the ability to do, so it's not a big problem. But yeah, that's another way of assigning these timestamps. You could also use a combination of both, or you could use a completely different method. So as long as it produces something that is unique for every transaction and that is monotonically increasing, then that should be a good timestamp value. So basically, again, the idea is that if we have some transactions, so let's say we have T1, we assign it a timestamp, we have T2, we assign that a timestamp greater than the first one. So based on these timestamps, we want this to become equivalent to a serial schedule where T1 executes before T2. So let's say, as we're looking at the transactions, we find, write A operation in T1, and then after that, in the same schedule, T2 reads A. So this means that T2 will read the value of A that was written by T1, which matches, that serial schedule where T1 executes first, because T2 is expected to read things that were written by T1. So in this case, these operations are valid according to the order that we're looking for. But if it was the opposite, for example, we have a write A in T2 happening first, and then a read A in T1 happening after that. So in this schedule, T1 is reading something read by T2. But if we want in the serial schedule for T1 to happen first, T1 cannot read something that is written by T2, because like T2 is kind of like in the future of T1. So it's almost like T1 is reading from the future, which cannot happen. So based on that equivalent serial schedule, the order of those read and write operations is not valid, so we'll not be allowing this to take place. So this is basically what timestamp ordering tries to do. Same thing if we have two writes. Like here we saw a read and a write, but what if we have two writes? Again, if we have write A and write A in two transactions, and again the timestamp of T1 is less than that of T2, so we want this to be equivalent to T1 executing before T2. If you have two writes, you expect the final value of A to be the one that was written by T2, which is true in this case. So this is a valid schedule. But if we have the opposite, that will not be valid, because in this case, the final value of A would be the one written by T1, which again does not match with the ordering of T1 followed by T2. All right, so again, talking about timestamp ordering, like I said earlier, we don't use locks. So any of the things that we've seen before with locking does not apply. In this scenario, each object that we perform, reads or writes on, this object could be a row, a table, an attribute, whatever level of of granularity we're talking about. Each object has to be tagged with some metadata or information. Since we're talking about timestamp ordering, the main information that we need to worry about is timestamps. So basically, aside from the timestamp assigned to each transaction, we also have a read timestamp for every object, which is basically the highest timestamp of a transaction that reads this object. And we also have a write timestamp, which is the largest timestamp of a transaction that writes this object. So for each object, we have to maintain these two values and then update them as we go. So the idea is, whenever we have a read operation or a write operation, we have to do some checks on the timestamp of the transaction that is attempting to do the read or the write, as well as the timestamps of the object being read or written. And based on those checks, we will either allow that operation to go ahead, or if that operation violates the serializability order that we have in mind, then we'll abort the transaction. So if we are trying to perform a read, so basically transaction Ti is trying to read object X. So what is the check that we need to look at? Basically, we need to compare the timestamp of the transaction, Ti, to the write timestamp on X. Pay attention that we're trying to read X, but we're looking at the write timestamp. Why is that? Because basically we want to make sure that we're not reading something that is written by another transaction in the future. In the future meaning a transaction with a higher timestamp. So the write timestamp of X is the timestamp of the highest transaction that wrote X. So if that write timestamp is larger than that of ti, it's a transaction that is trying to read x. This means that basically tx is trying to read from the future, which we should not allow. So in this case, we will just abort ti, and then we can restart it again. So when it restarts, it will get a new timestamp. So most likely it will be able to proceed at that point. If that is not the case, this means that the write timestamp is lower than or equal to the current transaction. So then things can proceed normally. We will allow the read instruction to take place. And then we need to update the read timestamp of x because it just got read by this transaction. So we need to update it to the maximum of its current value and the timestamp of ti. And once that is, has happened, then the next operation will go on and so on. So basically, this is what we do. At each operation, we do a check. If that check, indicates that the order is still valid, then we perform the operation and then we update the timestamp. If it indicates an invalid order of things, then we abort the transaction. So this is what we do in the case of reads. In the case of writes, we do something similar. So now ti wants to write object x. We have to do a similar check, but now instead of checking only the write timestamp, we have to check both the read and the write timestamps. If either of those exceeds what the current transaction is doing, then basically this transaction is writing something that has been read or written by a future transaction, which again violates the order that we're looking for. In that case, we abort the transaction, and again, we restart it later on with a new timestamp. Otherwise, we allow the write to go on, and then we update the write timestamp of x. So this is what happens in theory. Let's demonstrate that with an example. So here we have two transactions, T1 and T2, and suppose this is a schedule in which they execute. Of course, as we're going through, we don't really see the whole schedule. We just know what has happened up to that point, but we're listing the whole schedule here just for illustration. So the first thing that we said is for every object we need to maintain read timestamp and write timestamp. So we're going to put these here on the side for A and B, and we're initializing all of them to zeros, basically to indicate that none of them has been read or written at this point. So now we start. So T1 is going to start. So the first thing we do is we're going to assign it a timestamp. So let's say we give it a timestamp of 1, and we want to read B. So before we read B, we have to do the read check, comparing the timestamp of the transaction to the write timestamp of B. So in this case, since the transaction has a higher timestamp, it can proceed. So we're going to read B, and then we're going to update the read timestamp to the timestamp of T1. Now T2 is going to start. First thing, we're going to assign a timestamp as well. And then we're going to also attempt to read B. We have to make the same check. So we're comparing the timestamp of the transaction to that of the write timestamp of B. Again, it's greater, so we can go on. So the read is successful, and then we update the read timestamp to that of the transaction. Now we want to do a write B. So the write check, remember that it compares the timestamp of the transaction to both the read and the write timestamps of B. And again, no violation here, so we're going to do the write and then update the write timestamp this time to that of T2. Next, we're going to read A in T1. Again, the same check is fine. We're updating the read timestamp, followed by read A in T2. Same check, no problem. Update the read timestamp again. Same thing in T1. Same check is fine. Now we want to update the read timestamp, but the read timestamp is already at 2. So remember, the read timestamp is the max of the previous read timestamp and the current transaction, so it's going to remain 2. It's not going to go to 1. And then we have a write A, so we're going to compare the transaction timestamp with both the read and the write timestamps, in which case it's still fine. So we're going to update the write timestamp in this case after we do the write. And then both transactions are going to commit. So in this particular example, there was never any violation of the order that we have. So basically you can say that this schedule is equivalent to a serial schedule where T1 executes completely followed by T2, which makes sense. Like if you look at each of the objects, like B, for example, B is read by T1 and then it is read and written by T2 in this order. So T1 happened before T2 with respect to B. With respect to A, we have a couple of reads in both T1 and T2, But remember, reads are not conflicting with each other, so it's the same if we did all the reads of T1 followed by the read of T2, and then we have a write in T2 at the end, which in this particular case, nothing nothing depends on that. So again, it's as if we did all of T1 followed by all of T2. Let's see a different example. Here again, we have two transactions. This time we have just one object A, so we have read timestamp and write timestamp for A. Now let's start. T1 starts, it gets the first timestamp. We're attempting to do the read. We compare these values. The comparison is valid, so we don't need to abort. We're just going to do the read and update the read timestamp. We are going to do the write as part of T2, but before that we assign a timestamp to the transaction and then do the write check. Again, the timestamp is greater than both the object timestamps, so the write will be successful, and we update the write timestamp. Now we go back to T1 after committing T2. We want to do write A in T1. We're going to compare the timestamp to both the timestamps of A. In this particular case, we have a problem because the write timestamp of A is greater than the transaction timestamp. So basically means that T1 is trying to overwrite something that was written by T2, which violates the order that we're looking for based on the timestamps that we have. So since we have a violation, then what we're going to do is abort T1, and then we can restart it later on with a new timestamp. And if we assume that no other transactions are going to happen, then T1 should be able to proceed. So the benefits of this mechanism is that, like I said, it doesn't have any locks, so no transactions are ever waiting on each other, which means no deadlocking or anything like that. It always guarantees a serializable schedule. That's the whole point of this technique. The downsides of this approach, one downside is that you could have starvation, which means a transaction may never get to finish, especially if you're talking about a longer transaction that may conflict with other shorter ones. So like every time there's a conflict, you end up aborting and restarting that longer transaction, and then at some point during its execution, some other transactions come in, cause a conflict. The one with the older timestamp usually is the one that gets aborted, so it might keep getting aborted and never get to finish. So that's something that may happen in this scenario. Another issue is performance. We have noticed here that we maintain these timestamps, the read timestamp and the write timestamp with every object, and we have to keep checking them and updating them with every operation. So that's a lot of overhead. Clearly, like if we have too many objects to maintain, this overhead can become a lot of extra work that we need to do. So it's not ideal. So in scenarios where we know or we expect to be very little interference between transactions, for example, if the transactions are extremely short or they don't usually read the same objects or they don't access the same objects at the same time, or at least we don't expect them to, like it might happen but maybe not so frequently, we don't need all the overhead of maintaining all these timestamps, right? Like there could be other mechanisms that could work better in these scenarios. Those mechanisms usually are called like optimistic concurrency control mechanisms. There can be many different ways of doing optimistic concurrency control, but we're going to talk about just one such mechanism here. The one we're going to talk about today does so by maintaining a local copy of the objects that the transaction accesses, whether it wants to read or write an object. It will make a local copy of that object, and then any processing that needs to happen will happen on that local copy rather than on the original one in the database. And then at the end or near the end of the transaction, then it will write back that local copy back to the database. You can think of this as very similar to when you deal with source control software or tools, like something like Git, for example, right? If you want to change some code, you have the original database or the repository where the code resides. What you do is that you check out a local copy, right? And then you do all the changes that you want to do in your local copy. Someone else may also be working at the same time on their own local copy. There's no interaction. No one is interacting directly with the database copy after that original checkout. And then once you're done, you're going to do some sort of validation to make sure there's no conflicts. And then you push back the changes to the database, to the original repository, right? So this mechanism does something similar to that. So again, you check out a copy, work on it, and then write that back to the database, assuming there's no no violation or no issues. Of course, the difference is that for source control, you check for merge conflicts at the end, and you can usually do some merging between the files. Here, you're checking for serializability, and if that is violated, you can't do really merges, you have to abort. So in this technique, each object is basically read only once. So the first time we access any object, we're going to read it from the database, put it in the local copy, and that's the only time we're going to read that object. And then each object is also written only once at the very end, assuming everything goes okay. So because of that, we don't need to keep track of every read and write timestamps and all that stuff that we were talking about earlier. So let's look at a typical transaction without this new technique that we're talking about. Things usually look like this. You have a transaction, you have the database, you have all these read and write operations. They interact directly with the database. If we were talking about locks in the past, then this database will also manage all these locks and so on. Or you would have the timestamps as we were talking about in the previous technique. But with the one that we were about to talk about, the optimistic approach, especially using that local copy, this is what things will look like. So for a transaction like this, we're going to keep a local copy of the objects that we need. And then you can think of the transaction as split into 3 separate phases. The first phase is something that we refer to as the read phase. And this might be a little confusing because you can see here it includes reads and writes. So why do we call it the read phase? This naming is from the point of view of the database. So from the database point of view, you only read objects at this point. Whenever you read, like here, for example, we're accessing object A. So we're going to read object A from the database, put it into that local copy, and then do all the processing on the local copy. So all the database has seen was object A being read once, and that's it. So that's why everything here, even though it may include reads and writes, we call that the read phase because it only reads from the database. So basically the read phase is the majority of the transaction, which includes all the transaction's work, except that the work is happening on the local copy, not on the original in the database. And then once the read phase is done, you go into the validation phase. This is where you do some checking to make sure that the serializability order is not violated and so on. And if that is successful, then you go into the write phase, and this is when you write back the objects from the local copy back to the database. So from the point of view of the database, reading happens in the read phase, and then writing happens once in the write phase, and that's it. So let's talk about these 3 phases again a little bit more formally. So like I said, the first phase is the read phase. This is when data is read from the database to the local copy, and then any further processing or reads or writes happen on that local copy. Next, we have the validation phase. This is where we check that the serializability is not violated. And then third, we have the write phase, in which if the validation is successful, then we write that local copy back to the database. If the validation was unsuccessful, then we abort the transaction and then we discard the local copy. We never write it back to the database. So the read phase and the write phase are kind of straightforward. You're just reading or writing data. The main, tricky part of this technique is in the validation phase. What are the checks that we need to do? How do we ensure that serializability is not violated? So basically, when you reach the validation phase of a given transaction, we have to check this transaction against other transactions that are either in or past their validation phases. So transactions that are either being validated at this moment or have already been validated or even committed. Now we have a transaction on hand. This is the one that we're validating, and we have other transactions. So we have to do these pairwise validations between the current transaction and the past, and each of the past transactions. And each of those pairwise validations have to be successful in order to say that validation for this transaction was successful. So these pairwise checks or pairwise validations require certain information. So the information that we need is transaction timestamps. We need to keep track of the timestamps actually for each phase in all these transactions, like for each phase, when does it start, when does it end, and so on. We also need to keep track of the read set for every transaction, which is the objects that the transaction reads, as well as the write set, which are all the objects that the transaction writes. Given two transactions, the current transaction that we're validating and one of the other transactions, we have to look for one of three conditions. If either of these three conditions is satisfied, then we're going to say that this validation between these two transactions is successful. So the conditions are based on where these transactions are relative to each other in terms of their phases. So first case, we're validating Ti, and we have a previous transaction, Tj, that has finished its validation and has committed. So if Ti starts its read phase after Tj has completed its write phase, then we're going to say that this validation has been successful, because in this case basically there's no overlap between the transactions at all. So this is already like a serial schedule, like just between these two transactions. So Ti is completely after Tj. All right, if things are a little different, and let's say there is some overlap, specifically Ti completes its read phase after Tj completes its write phase. So there is some overlap in this scenario. So then this condition has an additional part which says that read set of Ti, there must not be an intersection between that and the write set of Tj. What does that mean? It means that Ti does not read anything that has been written by Tj. Why do we need to add that condition? Let's ask this a different question. What would happen actually if there is some overlap between the read set of Ti and the write set of Tj? If there is an overlap, it means that Ti is reading something written by Tj, right? So we may have something like this. We may have something write x in Tj, so the write set of Tj has object x, and we have read x in Ti. What we want to see is that we want to see if this is equivalent to a schedule where Ti completely executes after Tj, right? So if Tj happens first, then Ti should read the value of x written by Tj, right? Is that guaranteed to happen here? Let's see. Well, in this particular diagram, it looks like the write x is happening before the read x, so it looks fine. However, remember that the write x is not actually writing to the database. It's writing to a local copy. So the part that actually writes to the database happens in the write phase of Tj, so it may happen somewhere around here. So this means that it might be possible that the read x in Ti will not read the value written by Tj, but will read an older value, because it may happen before Tj actually writes to the database. So this means that we cannot guarantee that Ti will read the value written by Tj, which means that the serializability here is not guaranteed. So if we have something like this, then this validation will not be successful. But if we do not have any object that is written by Tj and read by Ti, then in this case, then even though there is an overlap between the two transactions, then we do not have a serializability issue, and we can say that the validation is successful in this case. The third scenario is, again, the overlap is greater. Specifically, Ti completes its read phase after Tj completes its read phase. So in this particular scenario, we have to add more conditions. So we have to say, and the read set of Ti does not intersect the write set of Tj, which is the same condition we just saw in the last time. But this is also not sufficient. We have to say, and as well, the write sets are also not overlapping, because here the overlap is much bigger in terms of the time for the two transactions. So we've seen the first condition, the read set and the write set. We've seen that in the second case. For the write condition, what this means is that there is some object that's being written by the two transactions, right? Again, if we want it to be equivalent to Tj followed by Ti, then the final value of that object should be the one written by Ti, right? So if we have two writes like this, write x in both transactions, we expect that the final value of x will be the value written by Ti. Is that something we can guarantee? No, because again, remember that the writing to the database doesn't happen where this operation is. It happens in the write phase of both transactions, and we don't have a guarantee on the order of what happens in that write phase. So it might be something like this, where writing x in Ti happens before it actually gets written in Tj, and we end up with the value from Tj, not from Ti, which violates the order that we want. If we have some variable x that's being written by both transactions, in this scenario, then we cannot guarantee serializability. But if that is not the case, if we don't have such a variable and we don't have the overlap between the read set and the write set, which is the second condition, then in this particular scenario, then the serializability will be guaranteed. So if either of those three cases is satisfied, then we can say that the validation of Ti with respect to Tj is successful. And if this is the case for every pair, like Ti with every other transaction, then in that case, Ti validates successfully, and we can say that now we can write back the local copy of Ti back to the database, and then Ti can continue. If either of the validations is not successful, then we must abort Ti, even though it has actually finished, like it has done all its work, everything in the read phase is completed in the local copy, but then it hit the validation stage and the validation is not successful, then we have to abort that transaction and discard the local copy. The advantages of this approach is 1, no locking, no transactions are waiting, no deadlocks, all of this stuff as we have seen before. We also don't have the overhead of maintaining and updating timestamps on every database object and checking with every operation. The validation only happens at the very end of the transaction, and it's very simple checks, I would say. So the overhead here is minimal. We also have a kind of like a side effect of keeping that local copy for every transaction is that we guarantee also repeatable reads. So if the same transaction is reading the same object multiple times, it will always return the same value. Well, unless the transaction itself updates, the object between reads. So that's a nice kind of side effect. And if it's truly no interference between the transactions or very little interference, like if all the transactions are not overlapping in time, or they have minimum overlap, or their read sets and write sets are disjoint, then in most cases the validation will be successful and everything will go through normally, which is basically the whole reason why we're going to this optimistic approach, right? Is the expectation that there's very little interference between the transactions. So if that's the case, then most transactions will be successful. The disadvantages of this approach is that if our expectation of little interference is not actually true, and there happens to be more interference that we thought, then we will have too many transactions being aborted after they've actually finished all their work, because we only check at the end. And if the validation is not successful, then we're going to abort the whole transaction, and it may end up in starving some transactions as well. Another disadvantage is that we have to maintain a lot of information. For example, we have to maintain read sets, write sets for every transaction. We have to also copy, all this local data into the local copy of each transaction. So there is some overhead there, but that's a compromise. So yeah, we've talked about 2 different concurrency control approaches today, and we're going to summarize what we talked about. So the first thing we talked about was the timestamp ordering technique, which relies on storing and maintaining read and write timestamps for every object, as well as assigning timestamps to each transaction. And then for each operation, we check the timestamps. If the timestamp of the current transaction is less than that of the read or write timestamp, then we have to abort the transaction and restart it with a new timestamp. Otherwise, it can go on and we have to update the corresponding timestamps as we go. And then we talked about the optimistic concurrency control and how that works using a local copy of the data for each transaction, and then some checks based on the different phases of the transaction, as well as the read set and the write set of each one. And based on that, if there's little interference, then things should usually go through successfully. Otherwise, in the validation phase, it should catch any violations in terms of the serializability and abort the transaction that causes that violation. We still have more to talk about regarding concurrency control, so expect one or more videos on that topic. But as usual, if there are any questions or if there's anything that needs to be clarified, please let me know in the comments and I'll try to get to that as soon as I can. If you found this video useful, please hit the like button. Please subscribe to the channel if you haven't done so already. And with that, thank you so much, and I will see you in the next video.